In this video, we're going to follow up with our last example with the trahedral and associated planes. And this example is about the osculating circle. So the osculating circle is a circle where if you're given a curve represented by the vector function r of t and a point P on that curve, we want a circle which lies in the osculating plane, and at point P, we want it to have the same tangent vector. So the tangent vector is the circle of the circle at point P is the same as that of the curve. It's going to be on the concave side, so that's the direction in which the normal vector is pointing. So the concave side of the curve. And its radius is rho equals 1 over kappa, so 1 over the curvature. So if you recall when we learned curvature, the curvature of a circle is 1 over its radius. So by enforcing that the radius of the circle is the reciprocal of the curvature of the original curve, then we're going to ensure that both the curve and the circle have the same curvature at the point P. That circle we call the oscillating circle, or the circle of curvature. So again, the osculating circle and the original curve share the same tangent line and the curvature at point P. So let's work out an example. We're given a helix, 2 cosine of t, 2 sine of t, 2 cosine of t, 3 halves t. And a point on the helix when t equals pi. So here is a plot of our helix with our point, our tangent vector, and our unit normal vector. We'd like to find a vector equation for the osculating circle. So our strategy is going to be, well, in order to find the equation of a circle, I need to know its center and its radius. And I need to know a little bit more because this is not a plane circle. I need to know the plane, the equation of the plane in which the circle lies. And I can get that by finding the equation of the osculating plane. So that means I'll have to actually calculate both these unit tangent and unit normal, or at least vectors that are parallel to the unit tangent and the unit normal. And then I will find their cross product. That'll give me a normal vector. And then I can choose a vector parallel to that to be the normal vector for the osculating plane, and I'll get its equation. Then I need to find the curvature of the helix at point P, because that'll tell me the radius of the circle. So now I know the plane in which the circle lies, and I know the radius of the circle, and I know this point P lies on the circumference of the circle. I know that the center is going to be on the normal line. So now I have all the information to find the center of the circle. So once I've got the center of the circle, I can get first a Cartesian equation, use the information for the plane, and then get a vector equation. So there's a lot of steps here, but all of these are good review. I wouldn't ask you to do all of this in an exam situation, but any one of these steps, given the other information, should be accessible. All right, so let's go through this one step at a time. So we're going to find a vector equation. Let's start with finding r prime for our helix and its length. So the helix is kind of a nice curve to work with because of the sine and the cosine there. The lengths don't depend on our parameter t. The lengths are constant. So the length of our prime is 5/2. So my unit tangent vector then is just r prime times the reciprocal of 5/2, which is 2/5. All right, take the derivative of t, and we can calculate its length easily again because of the sines and cosines, and now we've got a 0 in the k component. So now it's a simple calculation to calculate the unit normal vector. And so I've got the two vectors that lie in the plane, in the osculating plane, and I can just take their cross product now at that point. So P corresponds to the position vector when t equals pi. So when t equals pi, the unit tangent vector has components -4/5, 0, and 3/5, while the unit normal vector has components 0, 1, and 0. And if I take that cross product, I get the vector -3/5, 0, -4/5. Really, you don't need to do much work with such a simple cross product. You could, and I often do, if I have both t and n written that way, I just either imagine or just pencil in lightly an I, j, and a k above here, and then go ahead and calculate the corresponding determinants to see the value of t cross n. But I don't have to use that vector exactly. I can choose any vector parallel to t cross n to be the normal vector for my equation of the osculating plane. So I'm going to just clear out the fractions and make all the components positive. So I use 304, and our given point, its corresponding position vector to point P, it has components 0, -2, and 3 pi over 2. That just came from this position vector up there. And so if I just dot 304 with x, y, z, I get 3x plus 4z. And if I dot 304 with my initial vector, I get 6 pi. So there's my equation of the osculating plane. Next step is to calculate the curvature. So I'll need this information here. I'm going to use the formula for the curvature where we take the length of r prime cross r double prime and divide that by the length of r prime cubed. So the cross product, again, very simple cross product. And its length then, we get to take advantage of the sines and the cosines. So it's going to be radical 9 plus 16, which gives us 5. And so here's the formula. I already have the length of r prime. That's 5/2. So I'm going to take 5 and divide it by, well, 5/2 cubed is 125 over 8. Do some simplifying, and I'll get 8 over 25. So the radius is going to be the reciprocal, 25 over 8. So a little bit more than 3 and 1/8. So now that I know the radius, I know the normal vector, unit normal vector, I can find the center of the circle. Center of the circle is going to be where? Well, it's going to be on this normal line and a distance of 25 over 8 units away. And it's got to be on this side of the normal line because that is our concave side, or that's the side that the normal vector, where the normal vector points. So the position vector for the center is just going to be, well, our r naught plus uh, the radius of the circle times the unit normal vector. And working that out, I get the point with these coordinates right here. All right, so now we have the radius, we have the center, we know the equation of the plane where the circle lies. So the circle then would be the intersection of the sphere. Now in 3D, given the radius and the center, if I use the distance formula, I'm not going to get a circle. This is going to give me the equation of a sphere. I only want the great circle of that sphere, which is in the given plane. So I need to find the intersection of those two surfaces, and I'll just do some algebra, right? I'll solve for z in my equation for the plane. Go ahead and substitute that in for z in the equation of the sphere. That's going to leave me with an equation with only x and y. So now I've got an equation in x and y, but this is still not going to be enough for us to trace out the circle. We need to get a parametric or a vector representation of this circle. So we've got this equation, which was simplified, and we've got this expression that we use from the equation of the plane to get this. And what we're going to do, whenever we see something squared plus something squared equals something squared, we want to think about cosine squared t plus sine squared t equals 1. So the first thing I want to do is make the right-hand side 1. So I'll divide every term by quantity 25 over 8 squared. And let me write everything then inside the parentheses squared, right? So I have to simplify the 25 over 16. Actually, if I'm looking at the squares, I do the arithmetic. I get x over 5 over 2 squared plus y minus 9/8 over 25 over 8 quantity squared equals 1. So I'm thinking that what it's inside the first set of parentheses is cosine of t. What's inside the second set of parentheses is sine of t. So if cosine of t is x over 5 halves, that would mean x equals 5 halves cosine t. And the same idea here, I would have y minus 9/8 over 25/8 equals sine of t. So solving for y, I would get 25/8 sine of t plus 9/8. So I'm only left with my third component function for z. So I'm going to go back to my equation here and replace x with its component function or its parametric function over here. And so then I'll get z equals 3 pi over 2 minus 15/8 cosine of t. So the vector equation, and I'm going to use c here, or circle, is going to have those component functions. So I went ahead and used technology and plotted that circle. So I used that same plot 3D site. I was able to plot the osculating plane and the center of the circle and the actual uh, osculating circle. So you can see that the osculating circle near the point P is really a very good approximation of this particular curve. In fact, if I wanted to compare that with the tangent line, right? Again, here the orange line is the tangent line. Just a reminder of how I calculated that. I had previously calculated the unit tangent vector, so I could choose as a direction vector any vector which is parallel to the unit tangent vector. So I just cleared out the fractions here. And then we had our fixed point on the curve had a position vector of 0, -2, and 3 pi over 2. Now, I should be careful here, and I'm going to actually make a note that so let me put my little caution sign here. And I'm putting this because I made this mistake myself, and that is that I should have used different letters. Because it gives the impression that the t that we're using for the tangent line is the same as the t that we're using for the osculating circle, which is the same as the t that we're using for the original helix, and that's not true. So, let me just do a little erase here and to emphasize that, because if we ever wanted to compare these curves, then we should recognize that they depend on different parameters. So, for example, if I use S for the parameter for the osculating circle, because notice that point P corresponds to R when t equals pi, but to get point P is also a point on the circle. I can't use pi. What do I need to use? Looks like I need to use pi over, let me see, I need to use 3 pi over 2, actually. 3 pi over 2. So, see, r of pi, so that's t equals pi, corresponds to c of 3 pi over 2. So that is when s, the parameter s, equals 3 pi over 2. And then in my equation of the tangent plane, let me use yet a different number instead of t, a different number, different letter. Let me choose u, as the parameter. And then our point P corresponds to L of 0. So when U equals 0. So I shouldn't have used the T for each parameterization because it gives the impression that each parameter has the same representation. That's just not the case here. It's still a parametric representation of the particular curve. It's just that the point P doesn't coincide with the same parameter value. So as you can see, the tangent line deviates from the curve rather quickly because it doesn't have any information about the curvature. So we're adding information. You could see it was a lot more work to get that better approximation. And we can see that this circle of curvature remains close to the helix, at least in this view. Uh, it's hard to tell from just a shot like this, but certainly the curvature lines up, which is what we were looking for. Well, I hope you've enjoyed this video on the osculating circle example, and that wraps up our talk about the moving trihedral and its associated plane.